Okay, maybe we should just get started. If other people dial in, they can join in as we go along. So I don't have any other announcements really other than to introduce David, who's been gracious enough to fit us into his rather busy schedule and give us an update on OCO2. So I think I'll turn it over to him and then encourage people to ask questions either during the presentations or afterwards. So David, please go ahead.
Thank you, Tom. I'm going to go ahead and go through this package. You should all see it on your Adobe Connect screen. If you don't, scream bloody murder or send me an email or call me or something. My cell phone is open since I'm using the computer for audio here. I'm going to give a quick overview of the OCO2 mission, some of the recent results that it's collected. The title page here actually shows a standard nadir swath across Los Angeles, just to give everybody a quick understanding of some of the details of the spatial resolution of the instrument as it flies over something like a city. But you'll see more of that as we get into this presentation. I'm going to have a quick overview, which basically includes an overview of the current system status. The bottom line is that everything is nominal. Almost at the moment. We have a couple of upcoming issues, though, that we're going to be dealing with over the next couple of weeks. The first is a drag makeup maneuver, which is scheduled for tomorrow. I'll touch on that and why that's necessary a few slides down. And then a real quick thing, we actually routinely decontaminate the instrument. That usually knocks us offline for about a week. It turns out that we actually have to do an instrument reset along with a decontamination cycle by the end of the month, roughly. The nominal dates for that right now are the 30th through August 5th, but I found out yesterday evening that we might slip that 1 week further downstream so that we can participate in a little bit more of the first couple of weeks of the above campaign, which is ongoing in Alaska during this period. Let's see, I'll then give a quick overview of some of the ongoing science activities. In particular, what I'll do is make a very quick run through basically a sneak preview of the Science and GRL special collection that will be coming out later probably now early August at this point. Then talk a little bit about coming attractions. In particular, we've just developed a new data product. It's currently in production. It's called version 8. And we're in the process now of verifying the product and making sure that it's better than the one that's already out there. So I'll get through all of that, hopefully, before much of the hour has gone away. Okay, first thing I'll touch on is what are we trying to do here? Why do we need to go to space to make measurements of carbon dioxide anyway? And some of you have seen this. This is the movie that Goddard put out a couple of years ago, showing a 7-kilometer resolution nature run of carbon dioxide. The point to be made here is that as carbon dioxide is released in the atmosphere, it's basically dispersed by the winds in order to actually make very detailed measurements of carbon dioxide, in order to actually use atmospheric measurements of carbon dioxide as a way to help understand the carbon cycle. We actually need to combine a very dense network of CO2 measurements with the best atmospheric models to try to assess the impact of the wind. The current network is actually illustrated here. This is the ground-based network that ESRL GMD maintains and coordinates for the GAW network. Basically, we have a little over 150 ground-based sites right now that are making regular measurements of carbon dioxide. Most of those sites are located in North America and Western Europe. And neither of those areas are really the centers of action for the carbon cycle. And so the current measurement network, while certainly very good and absolutely essential as we move into the future, it just doesn't have the spatial coverage needed or the sampling frequency either to actually pull down the measurements we need to monitor the carbon cycle. So one way to actually get around this is to measure carbon dioxide from space. The way we actually do it with OCO2 is we make measurements of reflected sunlight as the sunlight basically bounces off the surface of the Earth and goes back up to the satellite and encounters lots of carbon dioxide and oxygen molecules along the atmospheric path. Those oxygen and carbon dioxide molecules absorb only certain wavelengths of light. If we use a high-resolution spectrometer and resolve that information, we can actually quantify the amount of carbon dioxide and oxygen along the path. We use that information in a remote sensing retrieval algorithm that basically which I'll talk about a little bit later on, to retrieve a quantity that's we refer to as the column average CO2 dry air mole fraction. This quantity, if you think about it, is basically what we're doing is just counting the number of molecules of carbon dioxide and oxygen between the sun, the surface, and the spacecraft along whatever path they happen to take. Then we use the oxygen to give us an estimate of the dry air quantity. We use the CO2 measurements to tell us what the CO2 column is along that path. And we basically ratio those to come up with this quantity. We need to make a measurement here that's accurate to about 0.25% to be of real value. That most of the sources and sinks that we know of CO2 produce variations in the column average CO2 dry air mole fraction that are of order of 1 ppm or smaller at a 400 ppm. So we need a very, very precise and accurate measurement. Because of that, we actually have to verify and validate the measurements against every possible source, validation source. You guys are very familiar with that. You know what's out there. We have class measurements for CO2 and other greenhouse gases. We have uplooking Fourier transform spectrometer measurements from Telecon stations. We have tower measurements, aircraft measurements. Air cores are a new capability. And then finally, we have GOSAT flying up there with us, and GOSAT measurements and those CO2 measurements can be cross-validated to actually further understand the quality of the two data sets. The OCO2 mission was launched in July of 2014, so it's just over 3 years old now. It's just past its third birthday. I'm glad to be out of those terrible twos. It was inserted at the head of the A train on August 3rd. It actually started making routine measurements on the 6th of September, so that'll be our real anniversary of taking data with the system. So we sit here right out in front of the A train with GCOM W1 just behind us, Aqua behind that, Calypso, CloudSat, Aura, and then Parasol's flying a little bit below the A train at the moment. We actually fly in a very, very tight formation with CloudSat and Calypso. In fact, we try to monitor and maintain our orbit track so that it's in very, very close alignment with the Calypso orbit track, shown here as a red line. And you can see the OCO2 orbit track, or I should say the nadir track for our orbit, where our nadir observations are taken, usually falls within about 5 kilometers of the Calypso track. And we do our best to maintain that alignment so that the Calypso's narrow 100-meter wide beam actually always shows up somewhere inside of our swath for the spectrometer. We do that because clouds and aerosols are an important source of contamination for our measurements. The Calypso measurements can be used to help characterize and qualify and validate our aerosol removal technique, our aerosol accommodation technique. Okay, the OCO2 instrument. How does this thing work? It's just a 3-channel imaging grading spectrometer. It makes measurements in the oxygen A band and 2 CO2 bands. Each channel looks identical, has the same basic optical path. We have a common telescope that feeds all 3 channels through a set of relay optics. The light is all focused on 3 narrow slits that then disperse the light, or the light then goes through the slit, hits a collimator, hits a plane holographic diffraction grating, and then the dispersed spectra are imaged by an imaging camera lens onto a focal plane array. The spectra look like those shown here. These are actually the first light spectra collected by OCO2 back in August of 2014. What we see here is that the spectrometers disperse the spectra along a 1016 element array of a detector. We use a silicon array in the A band, and we use Mercat arrays in the 2 CO2 bands. The cross-track dimension along the slit is actually an imager. We actually image 220 pixels along that slit. The middle 160 of them are divided into 8 cross-track footprints that are transmitted to the ground. So we basically have an imaging spectrometer that really is only returning 8 cross-track pixels at any one time by 1016 spectral elements in each of the 3 spectral channels. They're co-boresighted as well as we can make them. The system takes images of the spectra like this 3 times a second, 8 spectra times 3 times a second, 1016 footprints. Basically, it's a large amount of data that this thing generates. The actual sampling approach, as OCO2 orbits around the Earth about 14.5 times each day, we actually make measurements along a very, very narrow track. It's about 0.8 of a degree wide. The track is actually, the position of the track on one particular day is shown here in this image of this MODIS image. And you can see the OCO2 measurements are running just about down the middle of the MODIS tracks. This is MODIS Aqua, which is just behind us, 440 seconds. And so once again, we can use MODIS Aqua to help understand when we're hitting clouds and when it's really, really clear. We also basically then have used ground observations to help us make sure that we're pointing where we think we are. This is a track across the Strait of Gibraltar. 12 seconds of data. You can see the individual footprints here as well, as you did on the title slide. In each one of those footprints, we collect the 3 spectra. We collect 24 soundings each second as we fly over the sunlit hemisphere. Our objective wasn't really to try to have a wide swath and image the entire Earth. Our objective primarily was just to gather a lot of data with the hope that some of those data would be cloud-free. We collect about 1 million soundings each day, about 72,000 soundings in each orbit. In general, something like 10%, as we'll see, are cloud-free. But there are persistently cloudy regions. Here we're seeing the data from July. So far, this is the first 2 weeks of July, or first 13 days of July, shown here. We get reasonably good coverage of the Earth over a couple of week period of time, but you can see there are some persistently cloudy regions, such as the Asian monsoon here. This whole area, this is a cloud map showing, or a weather map showing where the clouds were on the 13th, on the last day this was taken, but they were pretty much persistently in this area for the entire time. We also see that we have problems getting measurements over South America here because the South Atlantic anomaly, high cosmic ray area is right here, and we've been throwing out those data. We're also getting some anomalous data down in the Southern Ocean here. We're not really quite sure what's going on there, but this is under investigation. We think, in fact, that what we're seeing down there is sea ice, and we're not modeling the sea ice very well in our retrieval algorithm. So that's basically just a real snapshot of what we see with this instrument. One of the things we do that you guys would be maybe familiar with, we actually do ground-based calibration campaigns each year. We do a vicarious calibration campaign in Railroad Valley. We just completed one of those campaigns on the 30th of June. We had a very, very successful campaign. We had observations on the 25th, 26th, 27th, 29th, and 30th. From GOSAT and OCO2 both. We had completely clear skies. It was slightly hazy on the 26th due to some fires that were just to the west of us. We usually have the Alpha Jet along with us, along with our ground-based complement of instruments, shown here primarily ground-based spectrometers we use to make measurements of the desert, the brightness of the desert floor. We also make a whole host of atmospheric measurements, including radiosonde observations. We have an up-looking Fourier transform spectrometer that sits on an EM27 that we use to monitor the CO2 and methane over the site as the spacecraft fly over. We use that measurement to assess the radiometric degradation of the instruments and cross-calibrate their onboard radiometric calibration standards. There was a short one-day salt and sea campaign at the end of this campaign on July 1st. We gathered good data there as well. All of these measurements are being, at this point, they're being analyzed. We learned yesterday the Chinese TANSAT, which was launched on December 22nd, also participated in this campaign. They reported yesterday that they had excellent overflights on the 26th and 29th, 26th, 27th, and 29th in coincidence with the GOSAT measurements, it turns out. It turns out TANSAT is flying just above OCO2 at the moment, clocked a little bit further back in the A train. So it did get some measurements associated with this campaign as well. Haven't seen that data yet, of course. Okay, how many measurements can we collect? Cloud-free measurements can we collect? This chart shows the number of soundings gathered per month on the left and per day on the right. I'm going to focus on the chart on the axis on the right. We make on the order of about half, basically about 50,000 to 75,000 clear sky measurements each day. The blue measurements here are the ones taken over the ocean in glint mode. The red measurements are those taken over land in glint mode, and the green measurements are the ones taken over land in nadir mode. To understand those modes, we need to understand that basically most of the time the spacecraft, or I should say a fraction of the time the spacecraft is looking straight down at the ground just below it. As the sunlight comes in and is scattered off the ground, comes back up to the spacecraft, and we measure that column. But that class of measurements, while very useful for getting through, getting more soundings in regions that are partially cloudy, the difficulty with that approach is that it produces almost no signal over the ocean. The ocean is extremely dark at the wavelengths that we observe. So over the ocean, we get far better data by using glint measurements, where we look at the bright ocean glint spot, where sunlight is specularly reflected from the surface of the ocean. And that class of measurements is a little bit more difficult to analyze, but actually produces far better results over the ocean, and actually produces pretty good results over land as well. Though it should be said that we get a little less coverage over land in glint mode than we do in nadir mode, typically, just because the longer paths associated with glint are more likely to be interrupted by clouds and aerosols. So we've managed to optimize the observing strategy during the mission. As you can see, early in the mission, we got fewer measurements than we're getting now. Basically, what we've done there is we now operate the system so that when it's over on an orbit that predominantly is over the ocean, we always take glint measurements now. In the past, we just either alternated between glint and nadir on 16-day repeat cycles, or alternated on alternate orbits. Finally, in November of 2015, we got to this mode where we can we alternate on every alternate orbit between glint and nadir when flying over regions that include land and ocean, but over regions that include only ocean, such as the Pacific and Atlantic Oceans, we stay in glint mode. So we're getting higher quantity of data. The new product that we're generating actually passes quite a bit more data than this, so we'll have to see what that actually turns out getting. But about 10% of the data in general are cloud-free enough to retrieve XCO2. We use a remote sensing retrieval algorithm. This is based on a full physics radiative transfer model that simulates the spectra given an input guess for the mixing ratios of CO2 and other trace species, aerosols, temperatures, and so forth. We use cables of gas cross-sections, aerosol and cloud optical property cross-sections. We use a solar spectrum file. That all goes into the forward model, as well as information about the viewing geometry and the sun's geometry. That generates a perfect high-resolution spectra, as well as spectral Jacobians, which give the first derivative of the spectra with respect to changes in the atmospheric state. We then have an instrument model that basically convolves these perfect synthetic spectra with our understanding of the instrument line shape function, our understanding of the geometric and radiometric calibration of the instrument, the polarimetric performance, to generate spectra that should look just like the ones being taken by the spacecraft if we have the atmosphere right. So basically, then the inverse model uses an optimal estimation approach to modify the initial guess for the state vector, given the spectra and the Jacobians and the space-based observations. It updates the state vector and then goes around and around and iterates until it comes to a converged state. It then spits out a retrieved state vector for its best guess state vector. We then average the CO2 over the column to get XCO2, and then we send it through the validation loop. So that's basically the approach that we use. Any questions on that before I go on? I guess everybody's finding their mute button, but in any case, I'll go ahead and proceed. The data actually looks like this. Some of you have seen this movie. I've presented movies like this in the past. This is an updated version showing OCO2 observations with about 4 days shown each second, showing the tracks of the spacecraft as it travels from south to north along the Earth. We actually observed the whole Earth at 1:30 in the afternoon. You can see there are some persistent regions that get very little coverage over the Amazon, over the Congo, where it's cloudy almost all the time. It's winter here, and so basically there's no sunlight up north, and there's a lot of clouds that are blocking our observations in this data set. As the spring progresses, we see a lot more sunlight and observations over the Arctic. We get good measurements during the summer actually during a lot of the spring and the fall as well over the Arctic. Notice how the measurements are showing the CO2 being drawn down as the biosphere wakes up and the trees and grasses start pulling CO2 out of the air. We can actually see this at fairly high resolution at this point with this data set. That basically is the kind of measurements that the spacecraft is gathering. As we move a little later into the winter season here, we'll see the buildup of CO2 in the northern hemisphere as the biosphere shuts down. We see stronger emissions during this period more distinctly over the places we expect to see emissions: China, India, northeast US, and Western Europe. So are these data any good? Well, the way we try to assess that on a regular basis is through comparisons with a number of standards. Our primary standard for connecting the OCO2 measurements to the in situ measurements made by GMD and its partners in the ground-based network is to use Telecon observations, measurements from ground-based uplooking Fourier transform spectrometers. We have about 21 of these operating around the world now in places as far south as Water, New Zealand, as far north as Sodankala, Finland, and actually Eureka, Canada, when the sun's up there. So we can actually make measurements over a wide range of latitudes and a number of different types of situations that allow us to help us understand what the biases in the data product are. We compare the OCO2 measurements to the Telecon measurements. For the version 7 product, our very first OCO2 product that we've generated, the comparisons were good but not perfect. We did have some outliers, especially during certain seasons. I'll talk about that a little bit later. But we had pretty good convergence or pretty good agreement with the Telecon measurements. We apply a bias correction, a geophysical-based bias correction that I won't have a lot of time to talk about. And after applying that bias correction, we improved the agreement with Telecon substantially to where the global bias is reduced to less than a part per million, and station-to-station biases can be a little bit larger due to a variety of factors, including basically a lack of perfect agreement among the Telecon stations themselves. One of the specific biases we've identified is most clearly seen in these measurements that, or these figures that Chris O'Dell produced, where he compares the OCO2 measurements to a multi-model mean. So he takes a host of half a dozen, I should say, carbon cycle models. He compares the OCO2 measurements to it, and usually we get pretty good agreement within a few tenths of a ppm. But what we're finding is that during certain seasons, especially during the northern winter, so let's say June, July, and August in the southern hemisphere, what we're seeing along the southernmost region that we actually are getting good observations, we're actually seeing a significant high bias in the OCO2 measurements. This was a serious source of concern over the last year or so. We actually discovered the source of the problem, and we've now remedied the problem. Basically, what happened is we discovered that very, very optically thin aerosols, basically the young layer in the stratosphere, it's only about 6,000ths of an optical depth thick when it's in its baseline state. When we're looking at these very, very large slant paths at high latitudes, even that small amount of aerosol actually can produce a bias in the OCO2 measurements. We had simply neglected to include that layer in this version of the algorithm. Then, just to add insult to injury, two large volcanoes, Wolf and Calbuco, went off in the summer of, or actually in the spring of 2015, and they subsequently generated a significant enhancement in the stratospheric aerosol layer over the southern hemisphere in precisely this region, and that contributed to the amplitude of the biases that we were seeing during the northern summer, southern winter of 2015. So as I've said, we've now actually implemented these aerosols in the algorithms. This shows some results from some early tests of the OCO2 algorithm. And as you can see here, the amplitude of the biases has been substantially reduced, but not eliminated entirely. There are other factors that were contributing to this as well, and we're still working on those. But once again, we're down to better than a half of ppm, at least in this particular bias. And quite frankly, we don't trust this multi-model mean to better than that. So this will be corrected in the next data product, which is, as I touched on earlier, is under production now. One of the other things we've done that several of you are aware of is that we not only process OCO2 data through our algorithm, we process the GOSAT data too, the data from the Japanese Greenhouse Gases Observing Satellite. It's been making measurements since June 2009. It makes only about 300 to 1,000 measurements, cloud-free measurements a day, but this data set is very long now, and it's a very useful data set for carbon cycle studies. So we've actually done our best to cross-calibrate and cross-validate the results from these two satellites to produce consistent data records so that we can actually integrate these data records. They agree now to better than 1 ppm. One of the kinds of things we've been seeing with OCO2, though, as we're flying over the Earth, are things like local sources. This is my hometown. This is Los Angeles. This is Caltech here that we're targeting with the target observations. This is the Armstrong Research Telecon station, which we also target regularly. These are just a couple of, this is a summer track and a winter track going across the Los Angeles basin. We see slightly higher concentrations of slightly higher values of XCO2 over the basin during the winter time, in part because the boundary layer is somewhat thinner and traps the CO2 in the basin a little better. In summertime, the boundary layer gets a little bit thicker, and the CO2 can escape over the mountains a little bit easier. But we're still seeing enhancements of 5 to 6 ppm over LA in individual passes with OCO2. It took us a year to detect Los Angeles with GOSAT, so this is a much more sensitive instrument. In addition to that, things like the Alberta tar sands. The tar sands are actually extracted from the ground in this region near Fort McMurray, but they're actually processed down here in the SAGD facility. We always see enhancements when we fly over the SAGD facility when it's clear. These enhancements are as large as anything we've ever seen over cities, megacities like Los Angeles, and is persistent. They basically have to burn about half of the tar sands in order to get liquefy the oil enough to get it into a pipeline. Another thing we've been seeing, Ray Nasser's done this work where basically we're looking at overflights of individual power plants. We were searching for individual power plants that we might have actually crossed over the top of. We didn't actually know about this particular one. We were looking for the plumes from these power plants over here, which are over in India. We, in fact, did detect those plumes, but we also detected a plume that was far, far more intense than we expected, 10 parts per million or so above the background. We then discovered that the brand new power plant was just brought online. I would have been a little embarrassed if we had missed this one. This one's called the Sasan Ultra Mega Power Plant. So like I said, we should have hit that one. But individual power plants produce enhancements large enough for us to see them with the OCO2 instrument if they happen to lie along one of our swaths. Another, on a slightly larger scale, a Finnish postdoc named Jani Hakarainen took our data, just simply detrended the OCO2 data, and has made global maps which show regions with large CO2 anomalies, large persistent CO2 anomalies. This data set covers basically a 1.5 to 2 year period. And what we see is enhancements over Northeast US. We see enhancements over Western Europe, just where we expect them, and over Southeast Asia, more or less, and I should say East Asia, where we expect them over Japan and China. In addition to that, we see very large enhancements in CO2 over the Sahel area south of the Sahara. To kind of understand and see if we can attribute some of these enhancements in CO2, Jani, who is a member of the OMI team as well, compared the OCO2 CO2 measurements to the OMI NO2 measurements, and found in fact there are very, very strong correlations between the NO2 observed in regions of strong fossil fuel production or use over East Asia, Western Europe, and over Eastern US. There wasn't so much of an enhancement in NO2 seen over the Sahel region. This is primarily due to biomass burning. The CO2 enhancements there are enormous, but the fires are lower temperature. Another area that's kind of caught everybody's attention is extraction regions again. This is the Persian Gulf. Once again, that CO2 release from flaring. We do see some evidence of that in the NO2, but not so much. And the spatial correlation is not perfect, though there are regions that are very, very well correlated here. The ocean response to the El Nino was also something we were curious about. The ocean is a significant source of CO2 at low latitudes when the warm water moved from the western to the eastern side of the basin during El Nino. Basically, it produces a very stable region. This shuts off the transport of CO2-rich water from the deep ocean up to the surface. We thought that might be detectable in the atmospheric signal. We know that from things like the Tau buoy network, one of the Tau network buoys, only one it turns out, was actually had a functioning CO2 sensor on it during this El Nino. It's out here just south of Hawaii. And that sensor actually, as the El Nino started, basically we saw an incredibly large reduction in the CO2 concentration near the surface waters as the ocean stopped pumping CO2 into the atmosphere. OCO2 at the same time saw a very small reduction, about a half a ppm change in the column. This large change in CO2 that the buoy was seeing is obviously restricted to the planetary boundary layer, and it shows up as a small variation in XCO2 as seen by OCO2. The baseline here was, of course determined from GOSAT measurements, so those are critical. Notice also that OCO2 sees an increase in the CO2 over the ocean basins just a few months into the El Nino, long before the El Nino recovered and the ocean started pumping CO2 back into the atmosphere. What's going on there? Well, what we think is going on, Moppet also saw an incredible enhancement in carbon monoxide at that time. That suggests that what we were starting to see over the ocean is transport off the land, where there was significant amounts of biomass burning going on, especially over Indonesia, but also a little bit over South America. So that was an interesting story that we did, in fact, talk about in the Science Special Series that's coming out. We also saw direct evidence of the fires over Indonesia. As you might recall, we burned they essentially burned down all that was left in Indonesia during the 2015-2016 El Nino. This was a very spectacular set of events that led to some incredible air quality issues. We then went and actually made these measurements, though, compared the measurements made by OCO2 to the inventories that had been put out for biomass burning based on fire counts and so forth. We found a very interesting thing, and Jens Hyman led this work. He basically found that the fires actually weren't emitting as much CO2 as we thought, and they were only emitting about 70% as much CO2 as the inventories had indicated. In this last period, these fires were nowhere near as bad as the ones in 1998 during that El Nino. Now, others are bravely taking the OCO2 measurements and assimilating them into global circulation models, into carbon tracer transport models and flux inversion models. What you're seeing here is the first step in a flux inversion activity. This particular work is being led by Brad Ware at Goddard, just showing you the OCO2 measurements being assimilated into his model. He's not doing a full flux inversion yet. To do a full flux inversion, we're adding to the let me go ahead and go through this again. We're also adding to the CO2 measurements of chlorophyll fluorescence. OCO2 also measures chlorophyll fluorescence simultaneously with CO2, and we can make global maps of the intensity of the chlorophyll fluorescence, which tells us where the uptake of carbon dioxide by land plants due to photosynthesis is the most strong. We see the tropics, of course, we see year-round activity there. Northeastern U.S., Western Europe, we see strong activity, Eastern Asia during the spring and summer months there. So you take that information, but this just this shows some of the chlorophyll fluorescence work. As we overfly a city like Des Moines, Iowa, the cornfields around it fluoresce very, very strongly, whereas the city itself has much less chlorophyll fluorescence and due to much less photosynthetic activity. If you make global maps of this, as Ying Sun has done, you basically see the strong chlorophyll fluorescence over regions where we expect large GPP, gross primary production, such as South and Central America, over the Congo. We see much stronger chlorophyll fluorescence than we do with, say, GOM2, partly because OCO2 has a much smaller footprint and is less contaminated by clouds. And so we're seeing results that are very consistent with what we're seeing from MODIS and so forth. Though chlorophyll fluorescence is a little bit more sensitive indicator of photosynthetic activity than greenness, which is inferred from MODIS observations. So, some, including Junji Liu and her team at JPL, have been assimilating these measurements and doing flux inversions in flux inversions. And so what did we see during the El Nino? What we saw compared to 2011, which Junji used as a reference year, is significantly enhanced CO2 emissions from the tropics, especially Africa, Indonesia, and South America. In her experiment, she's seeing, if you look at the differences between those 2 years, those are where we see the largest enhancements, though we do see small changes around the rest of the world as well. So we're making good progress there in understanding how the El Nino from 2015, 2016 actually affected the carbon cycle. And that paper is just about to come out, as I mentioned. We actually did see a very interesting story, though, coming out of this. By comparing precipitation anomalies with CO2 anomalies and GPP anomalies, we actually discovered that for 3 continents, Asia, Africa, and South America, we had 3 substantially different mechanisms working for that enhanced the release of CO2 in all 3 cases. Over Asia, we had a tremendously low rainfall, very, very low, very large negative anomaly in the precipitation. That was combined with very high temperatures, so a large temperature anomaly, especially over Australia, but also over East Asia. And that combination led to a lot of fire, which actually enhanced the CO2 in this range. Over Africa, we had near normal precipitation, but ultra high temperatures, and that actually basically just caused the biosphere respiration to actually exceed the photosynthesis. So the system, the biosphere there actually was trying to take up CO2, but respiration actually outran the CO2, leading to a very large outran the photosynthesis, leading to a large enhancement. Finally, in South America, we had a large negative precipitation anomaly, reasonably high temperatures, kind of a combination of the two. There, a very interesting thing happened. The chlorophyll fluorescence indicates that the biosphere simply shut down and stopped photosynthesizing. The plants just didn't have enough water. It was too hot, so they shut down their stomats and just stopped absorbing CO2, as far as we can tell, and that led to a large enhancement there. So all 3 of these, basically, as we say, we have 3 continents. We had 3 completely different stories. So if you had a theory for how El Niños affect the carbon cycle, you were probably right. It's just that you probably weren't right everywhere. So 3 different stories. Okay, how do we tell whether the flux inversions we're getting from these data are any good? Well, one way that Junji actually proceeded to do this was to look at aircraft profiles taken, those shown in red here, over the US and over the tropics, comparing results from the prior that she assumed in her flux inversions to the final retrieved results shown in black here. And what you can see is that in every case, the retrieved results, the inverted results actually move the CO2 concentrations closer to the observations where observations exist. We need far more of these measurements over a much larger part of the globe, especially in the tropics, to actually do a full validation of fluxes. This is an outstanding issue. We don't have a solution for this yet. We really need to work harder on this. You guys might be able to help. I'm going to run through now a very quick overview of some coming attractions in our new data product called Build 8. What is Build 8? Well, we've improved the calibration, accounting for the ice accumulation on the detector. This is an issue that's a common issue that we've been dealing with. Also a zero-level offset that produces in the A-band detector. We've improved the spectroscopy of oxygen and CO2 in this delivery. We've included stratospheric aerosols to fix that bias I mentioned earlier. We've changed from the ECM at WF to GEOS5 for prior meteorology. This really didn't change anything, but it was simply a convenience. We're hoping to use the GEOS5 aerosol predictions in a future version of the model. This just is a step toward that. We improved the CO2 prior, making it more consistent with that used by Telecon. We improved the land surface reflectance model in the previous in the previous data product. We assumed that all land surfaces were exactly Lambertian. Now we assume that they have a small non-Lambertian component to them. It seems to improve things over some of Telecon sites. We've done some better pre-screening, and this better pre-screening is yielding a lot more nadir ocean and high latitude land data. So you're going to see a larger data set coming down the pike in coming months. The important point to make is that we have now begun operational processing of this data set, the entire data OCO2 data product since September of 2014 will be reprocessed by the end of September. So if you notice your lights dimming, basically OCO2 is sopping up every spare computer cycle in the Northern Hemisphere to get this done. This is a very, very computationally intensive job. We're using our own clusters, we're using the NASA Pleiades cluster, and we're using the Amazon cloud to the extent we can. In addition to the standard processing, we're going to be trying to support a number of campaigns. The Ascends Alaska campaign is ongoing through this period. I mentioned earlier that we're going to miss a part of this because we have to do an instrument reset in the next few days. We're going to make that as short as possible and maybe move it later in this period so we don't impact as much of this campaign. The ACT America and ATOM campaigns are coming right up, and we're going to try to make sure we're in a good position to support those with the missions. You guys actually know about this. Okay, OCO2 isn't the only game in town for making greenhouse gas measurements. It was preceded by the Skiamaki instrument on Envisat, which operated from 2002 to 2012. The GOSAT instrument's been flying since 2009. We launched in 2014, and on December 22nd of last year, the TANSAT launched the first Chinese CO2 satellite. There's a lot coming up in the very near future. The Chinese plan to launch the Fingyong 3D satellite in September, if they can get that, if that happens. We're going to be watching very closely. Galfin 5 almost immediately after that. These two satellites are actually operational meteorological buses run by the Chinese. They have different classes of meteorological or CO2 sensors on them. TANSAT actually flies a grading spectrometer very similar to the one on OCO2. Fingyong 3D flies a Fourier transform spectrometer very similar to that on GOSAT, and Galfin 5 flies a spatial heterodyne spectrometer, which is essentially a stationary FTS. We've never been able to make one of those work at this spectral resolving power. It'll be interesting to watch the performance of Galfin 5 to see how it performs. Once these guys are up, also late in September, if anything goes like it should, Sentinel-5 precursor should launch finally out of Russia. It'll make measurements of methane, but not CO2. Once it gets up there with a 7-kilometer footprint over a 2,000-kilometer wide swath, it'll map the entire Earth out in methane. GOSAT-2 is scheduled to launch in late 2018, measuring basically with similar capabilities to GOSAT, but it'll have about 4 times the precision. It's precision much more like OCO2, and it's expected to get about twice as many measurements. OCO3 is scheduled to launch to be inserted onto the International Space Station Japanese Equipment Module in 2018 as well. As some of you have heard, it's been threatened for cancellation, but that isn't final yet. We've been told to complete the instrument and deliver it, and so we're going ahead and doing that at the moment, hoping for the best. As we move into the future, the French have finally confirmed the microcarb mission for entry into phase B and C, and so they're hoping to fly. This is a spectrometer similar to OCO2, but about half the size. It's actually a shell spectrometer. It'll fly in about the 2020 timeframe. They have now a partner. They partnered with Kinesis partnered with the UK Space Agency, which will provide the bus. Merlin will launch in 2021 on a small bus that's made by Kinesis. This will be a German-French mission to measure methane using an active LiDAR. GeoCarb is the first geostationary greenhouse gas monitoring system. This was approved in early December to go ahead. It's just about to have it next week. It actually has its system requirements review. If all goes as planned, it'll be deployed above about the longitude of the east coast of the U.S., about 85 degrees west longitude in 2022. GOSAT-3 scheduled for launch in 2023. We're not quite sure what GOSAT 3 will be carrying. It probably will not include the same class of instrument carried by GOSAT 2 and GOSAT. It probably will be a broad swath instrument, either an imaging FTS or a grading spectrometer. I think the latter is gaining more favor in that group, but that's to be seen. Then Sentinel, this should be Sentinel-7. The Europeans are putting together a constellation of greenhouse gas measurement satellites that will be launched starting in 2025. They want the entire constellation of 3 or 4 satellites launched by 2026 now. So that will be our first real constellation. And then in the future, hopefully, we'll be seeing some active CO2 monitoring instruments flying. So we have a very significant series of measurements going forward. It's important to note, though, that up until, except for the Sentinel-5, all of these instruments up through GeoCarb are scientific satellites, not operational satellites. And so we'll be trying to string these guys together into an ad hoc constellation to try to meet our measurement needs until we get the dedicated constellations launched in the late 2020s and early 2030s. So that's about where we are. Just to summarize, OCO2 was successfully launched on the 2nd of July 2014. It started its first extended mission on October 16th of 2016 with a healthy spacecraft and a healthy instrument. It's now returning on the order of about 100,000 full column measurements of XCO2 each day over the sunlit hemisphere. These products are being validated against Telecon and other standards to assess their accuracy. Over 34 months of data have been delivered to the Goddard Earth Science Data and Information Services Center. You can pick the data up there. It's easy to come by. You just need a computer with a large disk. We're delivering, this is many gigabytes every day. Let's see, the products are now being used by the CMS team, as you know, and by others in the carbon cycle community to identify and quantify CO2 sources and sinks. Hopefully, all of you will be able to jump in and help out as time goes on. So with that, I'm going to go ahead and quit and take questions. Any questions?
Thank you, David. I had a question on the reprocessing of the V8. Are there any particular areas where you expect larger impacts than others, or particular, meteorological conditions?
Yes, we actually do expect significant improvements in the Arctic and over the Southern Ocean. The version 7 product had some artificial screening constraints over the Southern Ocean, which literally threw out everything at zenith angles larger than 65 degrees. That constraint has been removed, and so we're going to see a lot more data make it into the system for processing over the Southern Ocean. Over the Arctic, the cloud screening has been improved over at high latitudes especially, though also at low latitudes, and is expected to yield substantial additional data, so much that we think that it will very much stress our ability to process it all. We've been processing every cloud-free sounding in our reverse stream so far. We're hoping to be able to keep up with that as we move forward, but we expect to see substantial improvements in those areas. We'll see some improvements over South America just due to the fact that we've had a better screening capability over the South Atlantic anomaly to screen out cosmic rays. Unfortunately, in our previous data product, we have a cosmic ray screen associated with the actual spectra that we process, but we did not employ that screen for our cloud screening processor. And our cloud screening processor would actually see a cosmic ray and interpret it as a bad data and throw out that sample. So that's been fixed as well. So we expect to see improvements there. So you'll see improvements over a large number of areas.
Thanks. Any other questions?
Yeah, Dave, this is John Lynn. We have a CMS project focusing on the western U.S. I'm curious on your thoughts on the use, especially of XCO2 over complex terrain. Is that really difficult task, or how would we filter for it? I noticed that a lot of the warn levels are above 15.
Yeah, complex terrain is a nightmare. In version 7, it didn't work out very well. We think we understand why at this point, and we're looking into it. Build 8 will also have some issues over complex terrain, though it might do a little better. We're seeing a little bit better yields over complex terrain. The quality of the data we have not yet analyzed, so I'm not going to make any strong statements about the actual data quality. I'm just hoping that there's a little bit more to analyze over complex terrain. In general, what we found in our initial processing is that there appears to be a small pointing error in the OCO2 data. And to give you an idea of that, the individual footprints for OCO2 measurements are, if I dash back up to my title slide, are basically 2.5 or 2.25 kilometers long and 1.3 up to 1.3 kilometers wide. You can see them here. So basically, they have finite size, and we actually have a requirement to align those footprints to within about a half a footprint in terms of geolocation. Over complex terrain, that's an issue. And if we tell our prior we're looking in a particular place relative to a digital elevation map, and we're not looking there, it will introduce a bias or an error in the data. The error can be so large that the processor might throw it out, throw out the data, and I think it's just bad data. You can see an example of that shown over here as we start moving up the side of the mountain. Over the next few months, one of the first things we're going to be looking at for our next data product is ways to improve our pointing, maybe significantly, so that in regions of complex terrain, we can get better products. Over time, we'll be testing out that algorithm, and we'll be able to deliver in small quantities corrected data products for use by those who are interested in this. So that might be your best hope. But once again, this is a in-process issue.
What I'm hearing, Dave, is that for V7, we should try not to overinterpret the Warn levels above 15.
I wouldn't. Actually, you have to be careful about Warn levels. Warn levels are derived basically by looking at variations relative to the mean in a given area, a given small area. And in regions with strong topography, the Warn levels just don't work. I would just ignore them. I would use the quality flag. Quality flag is bad. I would just ignore the data sample. If the quality flag is good and the Warn level is very high, use your best judgment. I wouldn't use the Warn level.
Thanks. I think right now, when we looked at the western U.S., it moves most of the mountains.
Yep, it sure does. All of the western U.S. has high Warn levels. Sorry about that. That technique worked beautifully over much of the world. It didn't work over the western U.S. Sorry about that. It's bad for me because I actually live there.
Thanks for the insight.
So David, can you hear me? This is Lucy Hutira.
Yes, Lucy.
So I had a question about the data coming from land-water interface. We've seen some anomalies right at that transition space, and I'm wondering if the new data reprocessing will help address that, or if there's been any progress made on that problem.
The short answer is we hope so. We've noticed those differences as well. We're specifically testing for them right now, testing the level 8, the version 8 product for that. It's still a challenging area. When we have, for those pixels that actually overlie land and ocean in a given pixel and given footprint, I would say in version 8 I wouldn't trust those either. But those on either side of that pixel should be pretty good. And let me explain why that is. Our detectors aren't entirely linear. And when you go across a land-water interface, you have a massive change in the reflectance of the surface, typically. We cannot correct on a part of a footprint. we basically just get a bucket. Think of each pixel or each footprint as a bucket of photons. We just look at the amount of photons we have in there, and we do a nonlinearity correction on that mean value. What we can't do is a nonlinearity correction on the first half of the bucket, which ended up over the ocean, and the second half that ended up over land. And so we end up in those cases introducing an incorrect correction for nonlinearity of the detectors that can actually be several percent. And that's an error or an uncertainty or whatever you want to call it between the continuum and the cores of the lines, because they sample different parts of the detector. The cores of the lines are always linear. The continuum gets to be very nonlinear over bright scenes. So this is an issue we're working on. We at least hope to be able to quantify the errors better. We hope to salvage pixels that don't have very, very large brightness contrast in them. Those that do have large brightness contrast, I think we're just going to have to flag. So I hope that answers your question. I know what you're after here. Boston is a very important study area for you guys, and it's got this damn ocean next to it.
So do most cities. Whether it's ocean or lake or river, they all seem to have water next to them. Most cities have lake, river,
so
ocean.
That's going to be a challenge for us.
If you're comfortable commenting, I'd also
we might
love. Go ahead.
I'm not hearing you.
Sorry, I'm calling from my cell phone. If you're comfortable commenting, I'd love to hear some more impressions about the prospects for OCO3.
It's not that I'm not comfortable commenting, at least in not more than I would be just for sake of polite company. We have been asked to complete the instrument, complete the testing of the instrument, and put it on the shelf for right now. So we will have a functioning, well-calibrated instrument, once again, spending some time in a box. This isn't the first time that OCO3 was canceled. OCO3 was also canceled a couple of years ago. We were able to keep the system alive and to pick it up again and to complete the calibration this year. We're intending to complete the calibration of the system and have it ready to deliver to SpaceX for integration in the trunk of the Dragon module by December of this year. So that's the current plan. We have resources to do that. It turns out that the launch is also paid for already. And so the Dragon capsule is going to fly either with OCO3 sitting in the back or not. And it'll be somebody's whim as to which way it goes. The Japanese equipment module's exposed facility happens to be a shelf. We could store it there. But once again, we would have to actually abide by any specific language that we are given by Congress there in any budget that's actually passed. I've seen the House of Representatives budget that just was passed. It does not include any funding to fly or operate OCO3. And so that's not especially good news for us. But once again, the second foot hasn't fallen yet because the Senate hasn't ruled on this. So anything could happen. This is just the way things work. Between now and then, the team's going full blast. There's no stopping. Does that answer your question as well as I can?
That's super helpful. That's super helpful. Thank you.
Okay, unless there are other questions, I guess we were just about out of time, so that worked out beautifully. So thank you again, David. This is a very helpful presentation. I'm sure it'll be very useful for everybody who's planning to use this data in their inversion studies.
I look forward to collaborating with you guys.
Great. Okay, thanks again, and goodbye, everybody. And I'll follow up with an email to try and add some future meetings. Thanks, everybody.
Thanks all.